Hello everyone. In today's lecture, we are going to discuss about SR flip-flops. So in the previous lecture, we have discussed about SR latch. SR latch is the base for SR flip-flop. If you haven't watched that video, please visit that video. Now coming to SR flip-flop. Flip-flops are digital circuits that store a single bit of information and holds its value until it is updated by new input signals. They are used in digital systems as temporary storage elements to store binary information. The same thing latches does. So what is the difference between flip-flop and latches? Flip-flops are latches with clocks. If we consider a clock, if you go and refer the symbol of a clock, symbol of a latch, there won't be any clock given. So latches work without clock. They are level triggered. Flip-flops need a clock. So flip-flops are latches with clocks. They are commonly edge-triggered clocks. They use as edge-triggered clocks, either positive edge or negative edge. That is the leading position of a square wave pulse or the trailing edge of a square wave pulse. Flip-flops are useful for design of synchronous sequential circuits. And do you know why these flip-flops are being used? It is used basically in storage elements. It is used in counters, frequency dividers, and many other DSP, digital signal processing circuits for data sampling, buffering, synchronization of data. It has been used in shift registers. So all these applications are common for most of the flip-flops. Now coming to SR flip-flop, if you see this symbol in an SR latch, this clock will not be available. If you see a flip-flop is a latch with this clock. So we have this clock signal and this shows that it is an edge-triggered clock. This is the circuit diagram of a SR flip-flop. With NAND gates, we have realized this. If you see here, if you forget this part and if you consider this part, this is an SR latch. This part, these two NAND gates together forms an SR latch. And to this SR latch, instead of giving S and R directly as one inputs, we have given it through a NAND gate. S and R are given to two NAND gates as one inputs each, and clock forms the other input. So this is the circuit diagram. That is, this NAND gates along with the SR latch gives us a SR flip-flop. And this is the truth table of SR flip-flop. Once if you understand the SR latch, working principle of SR latch, what happens when S is equal to 0 and S is equal to 1? Then S is equal to 1 and R is equal to 0. S is equal to R is equal to 0 and S is equal to R is equal to 1. So please refer the working principle of SR latch in the previous video, and the same applies here. When there is no clock, this means when there is no clock, right? 0 0, there is no change. So the same thing which is available there in latch. So when we give a clock for 0 1, the output will be 0, Q will be 0 and Q dash will be 1. When it is 1 0, Q will be 1 and Q dash will be 0. When it is 1 1, it becomes a forbidden state. This is the characteristic table of a flip-flop. So what is meant by a characteristic table, right? Truth table, it shows the working principle, working when the inputs are given, what will be the outputs. And characteristic table is one wherein the inputs and the present state is given and the output is being calculated. So the inputs here are S and R and the present state is Qn. So when we consider these two inputs and one present state, we have three inputs altogether, and so we have 8 different combinations. So when the inputs is 0 and 0 and Q present state is 0, what will be the next state? When the inputs are 0 and 0 and the present state is 1, what will be the output? So this study of this, that is when the inputs are 0 1 and 1 and 0 and so on with a particular present state, what will be the next state? Study of this is known as the characteristic table, and from this characteristic equation will be derived, which is used to generate the logical circuit. So this is a very important table, characteristic table, which helps us to generate the characteristic equation. This is the excitation table of a flip-flop. So this excitation table is very important in designing counters and other circuits. So excitation table is one which states that when present and next states are given, what will be the inputs. So this is derived from the characteristic table. When you see the present state is 0 and next state is 0, present state is 0 and next state is 0. Here we have two different combinations, that is 0 0. Here also present state is 0 and next state is 0. When we see here S and R, in this case S is 0, R is 1. In this case S is equal to 0, R is equal to 0. So S is same for both the cases. When Qn is equal to 0 and Qn plus 1 is equal to 0, S is 0 always, but R is varying. R takes the value 0 when at one instant and takes the value 1 at another instant. So that is what is mentioned here. When Qn is 0 and Qn plus 1 is 0, that is next present state is 0 and next state is 0, S is 0 always, but R is toggling. That is at one time it is 1 and another time it is 0. So we mark it as X. That is a don't care state. Either it could be 0 or it could be 1. Similarly, when Qn is 0 and Qn plus 1 is 1. So similarly, we can check all these things. Qn is 0 and Qn plus 1 is 1. Here we have the case, right? So S is equal to 1 and R is equal to 0. So from the characteristic table, S is equal to 0, R is equal to 0 when Qn is equal to 0 and Qn plus 1 is equal to 1. So this is how an excitation table is drawn from the characteristic table. So first, based on the working principle, we will be drawing the truth table. From the truth table, we will draw the characteristic table. The characteristic table is one which gives the output or the next state when the inputs and the present state are given. Once after drawing the characteristic table, we will be deriving the excitation table. Excitation table gives the information that when present and next states are so and so, what will be the inputs. Once after deriving the excitation table, it is now time to draw the logical circuit. In order to draw the logical circuit, we need the logical expression or the Boolean expression. So the Boolean expression can be derived using a K-map. So this K-map is drawn from the characteristic table, from this table, right? The inputs are S, R and Qn. We have three different inputs, S, R and Qn, and this is the output. So characteristic table is one which gives us the equation for the output. So just we'll be drawing the K-map for this table. Three inputs are given. This is the output. This will be plotting it. Since it is a three variable K-map, we'll be having 8 cells and we'll be filling the values, group it and then form the equation. In this row, only S is the common term and here the common term is R dash and Qn, right? 0 and 1. 0 belongs to R dash and Qn belongs to 1, right? So we'll be getting an equation like this. From this, we can draw the logical circuit. This is all about SR flip-flops. Now it's time for assessment. What is the difference between a latch and a flip-flop? list few applications of flip-flops. Thank you.